Welcome back to A Slice of Physics. Let's now take a look at electric field lines and equipotential lines. We will first see what electric field lines are and understand that they are a representation of electric field in a region of space, while vectors only indicated the field at a given point. We will see how we can go from electric field lines to vectors at various given points. Then we will discuss equipotential lines. We'll see that these are lines that connect points of equal electric potential. The gravitational analogy of these would be points that connect equal gravitational potential, which translates to equal altitude from mean sea level, and you would have seen these as contour lines on terrain maps. And then we'll look at how equipotential lines and electric field lines are related. Let's start with recapping what the electric field looks like around a positive charge. So if I have a positive charge sitting over here, and I want to know the electric field at this point, and let's say this point, we know that electric field always points directly away from a positive charge, so it's going to be an arrow like that. Once we come to the second point, because the second point is at the same distance from the charge as the first one, the magnitude of the electric field will be the same. It still points directly away from the positive charge, so it'll be pointing straight down, and it'll be the same length of the arrow because the magnitudes are equal. This third point will again point directly away from the charge, so diagonally down and right like this. But since the distance is now about twice what the previous points were, the field would drop to 1/4 of what it was. Remember the 1 over r squared relationship, so it'll be something like that. Alright, having these three vectors might give me a little bit of an indication of what's going on about the electric field around this positive charge. But if I want to get a full field, I'll have to select many more points and draw vectors at all of those points. Each of these vectors, it's important to note, only represents the electric field at a given point, and that's the point at the tail of the vector. It doesn't say anything about the electric field anywhere else. Electric field lines, on the other hand, are a way of representing electric field in a region of space. So if I have that same positive charge, the electric field lines would be represented something like this. Now, at first, you may think that all I did was drew many more vectors that begin at these points, but I didn't do that. These are field lines that don't really have a starting or ending point, but tell me about the electric field in a region of space. And for a point charge, these are straight lines like we have shown. It gets more interesting if I take a dipole situation, so let me take that over here and tell you a little bit more about the properties of electric field lines. So I've got a positive charge separated from a negative charge. That's what creates an electric dipole. And the electric field lines for a dipole will look something like this. It points away from a positive charge and towards a negative charge. It'll start curving as I go up like that, and the field lines will get farther apart as I go farther away from the charge. So a little more clustered over here, and as I go farther away, it gets farther from the previous line. And negative charges will have electric field lines pointing toward it like this on this side, and the positive charge will have field lines pointing away from it like this. So this is the combination of the electric field of these two charges. So at any given point, these field lines represent the electric field that's a vector sum of the field from the positive charge and from the negative charge. So this gives me a representation of what the electric field is in this region. Now there are some properties. The denser the field lines are, denser field lines implies stronger field. That's quite intuitive. More field lines closer to the charge give me a stronger field. The second fact I have is the arrows give me the direction of the electric field. And if I want to get the field at a specific point, so let's take this point over here, this point over here, and this point over here. At each of these points, the electric field would be tangent to the curve that is the field line. So the way tangents are defined is lines that skim the curve at just one point. Or you can think of it as if you zoom in and zoom in and zoom in, any curve ends up being a straight line. So it'll be that line. So the tangent line over here might look something like this. It's a straight line that touches the curve just at that one point. However, if I want to get the vector at that point that is tangent at that point, but it has to begin at that point. So this is what the electric field vector at this point might look like. So it's tangent to the curve, begins at that point, and it has the same direction as the direction pointed by the curve. Similarly, the electric field over here will be tangent to the curve over here, but it's not quite as strong. So tangent will go like this, and it's going to be slightly shorter than the previous one. How do we know it's shorter from the electric field lines? Well, the density of field lines, the neighboring lines at this point are a little bit closer than they are for point A, are a little bit closer than they are for point B. So we know that the field here is weaker. And then when I come to point C over here, tangent to this curve is just going to be horizontal to the right. And because these lines are getting sparser now, the field would be even weaker than it was at B. So we had the first fact that the denser field lines indicated a stronger field. The second thing that it indicates that at any point, if I want the electric field vector, electric field is tangent to the field line and has the same direction as was indicated by the field line. So hopefully you can now see that these vectors only indicate electric field at the points at which they are shown, whereas the field line gives me a representation of electric field in that region of space. All right, now let's take a look at equipotential lines. These are lines that connect points of the same electric potential. So if I have a positive charge sitting over here, the electric potential of a point charge, you'll remember, is given by this equation, V equals K times Q over R. So for this one charge, if I'm at a constant distance around it, the electric potential is going to be the same. So the equipotential lines for a simple point charge are simply circles that are centered at the charge. So that may be my 100-volt line, that may be my 90-volt line, that would be my 80-volt line. Remember, the positive charge sits at the top of a hill that gets shallower as you get farther away from the charge. So my equipotential lines will keep getting farther and farther apart as I go farther away. So just for illustration, let me put some numbers over here: 100 volts, 90 volts, 80 volts, 70 volts, and so on. And I know that the electric field lines look like this. They always point directly away from the positive charge. So in this context, we can say that the electric field lines are radials, whereas the equipotential lines are concentric circles around the charge. Let's see if we can see any properties that relate these two things. We know that when a radius touches a circle, it always cuts it with a 90-degree angle. The tangent and radius are always perpendicular to each other. So this tells me that the equipotential line and the electric field line will be perpendicular wherever they meet. So that's our first point over here. So let's mark that. Electric field is perpendicular to equipotential lines. Second, that previous relationship we discussed about the density of field lines applies here too. Wherever equipotential lines are more densely packed, electric field would be stronger. So electric field is stronger where equipotential lines are closer together. So based on our recent discussion about field lines, that implies that electric field lines will be more densely packed when equipotential lines are more densely packed, which happens closer to this charge. As you get farther away, the field lines are getting farther away, the equipotential lines are getting farther away also. The third thing we see here is the electric field always points from high to low potential. So to take another example to drive this point home, if I had a single negative charge, I would have equipotential lines that are circles around it, again denser, closer to the charge, and moving farther away as I move farther away from the charge. And these values, to make up some numbers, might be minus 100 volts. Remember, the potential around the negative charge is always negative, which is why we say it sits at the bottom of a valley, minus 90 volts and minus 80 volts. And you know that the electric field lines around the negative charge all point directly toward it as straight lines. So these are my field lines. Let's see if the relationships we came up with hold for a negative charge as well. So let's take some points, again perpendicular, wherever an electric field line meets an equipotential line, it's perpendicular, so that works for the negative charge as well. we see that the electric field lines are more densely packed closer to the charge, where the equipotential lines are also more densely packed, so that matches. The electric field is stronger where equipotential lines are closer together. And then let's see if electric field still points from a high to low potential. So we got minus 100, minus 90, minus 80. So the potential is getting higher. Smaller negative number means higher as we go farther away from the charge. That's why we said the negative charge sits at the bottom of a valley that gets shallower as it goes farther out. And we see that the electric field line points from higher potential to lower potential, which is towards the negative charge. So for the positive charge, it had to point away from the positive charge to go from high to low potential. For a negative charge, it points toward the negative charge to go from high to low potential. So this fact is always true. All right, to recap, we learned about electric field lines and equipotential lines in this video. We started with electric field lines, which describe the electric field in a region of space, and saw how they are related to vectors, which describe the electric field at a given point. We saw that at any point the electric field vector is tangent to the electric field line, and then the magnitude of the field is larger where the electric field lines are clustered closer together. Then we learned about equipotential lines as lines that connect points of equal electric potential, and then we saw how they're related to electric field lines. We saw that field lines are perpendicular to equipotential lines. We then saw that the electric field points from a higher potential to a lower potential, and we saw that the electric field is stronger where equipotential lines are closer together as well. Thank you, and I'll see you later.